Oh my goodness, is this string of YouTube videos gonna ever end today? This is my third in 2 days. Change of scenery, just wanted to show you all as a warning. If you do get into the no-till mulch method, you may want to avoid the situation that I'm in currently, where you can see 3 piles of mulch, 1, 2, 3. It's becoming an issue at this point, I have to admit. But yeah, I just wanted to give you all first-hand look at my life. It's definitely, it's pretty much as raw as it can get at this point. And I'm riding the surf wave, I'm just riding it. So, please don't imagine that I've got it all together, because I'm really just doing the best I can, as I'm sure you all are. So let's just continue with Maxwell's treatise on electricity and magnetism, where I left off earlier today, completing the preface. Yeah. So this is the preliminary, he calls it, preliminary on the measurement of quantities. Every expression of a quantity consists of 2 factors or components. One of these is the name of a certain known quantity of the same kind as the quantity to be expressed. One of these is the name of a certain known quantity of the same kind as the quantity to be expressed, which is taken as a standard reference. The other component is the number of times the standard is to be taken in order to make up the required quantity. The standard quantity is technically called the unit, and the number is called the numerical value of the quantity. There must be as many different units as there are different kinds of quantities to be measured. But in all dynamical sciences, it is possible to define these units in terms of the 3 fundamental units of length, time, and mass. Thus, the units of area and volume are defined respectively as the square and the cube, whose sides are the unit of length. Sometimes, however, we find several units of the same kind founded on independent considerations. Thus, the gallon or the volume of 10 pounds of water is used as a unit of capacity as well as the cubic foot. The gallon may be a convenient measure in some cases, but it is not a systematic one, since its numerical relation to the cubic foot is not a round integral number. In framing a mathematical system, we suppose the fundamental units of length, time, and mass to be given, and deduce all the derivative units from these by the simplest attainable definitions. The formulae at which we arrive must be such that a person of any nation, by substituting for the different symbols the numerical value of the quantities as measured by his own national units, would arrive at a true result. Hence, in all scientific studies, it is of the greatest importance to employ units belonging to a properly defined system, and to know the relations of these units to the fundamental units, so that we may be able at once to transform our results from one system to another. This is most conveniently done by ascertaining the dimensions of every unit in terms of the 3 fundamental units. When a given unit varies as the nth power of one of these units, it is said to be of n dimensions as regard to that unit. For instance, the scientific unit of volume is always the cube, whose side is the unit of length. If the unit of length varies, the unit of volume will vary as its 3rd power, and the unit of volume is said to be of 3 dimensions with respect to the unit of length. A knowledge of the dimensions of units furnishes a test which ought to be applied to the equations resulting from any lengthened investigation. The dimensions of every term of such an equation with respect to each of the 3 fundamental units must be the same. If not, the equation is absurd and contains some error, as its interpretation would be different according to the arbitrary system of units which we adopt. So far, pretty straightforward, but trust me, it's about to get deep, folks. We're about to get into the formulas pretty soon. The 3 fundamental units: length. The standard of length for scientific purposes in this country is 1 foot, which is the third part of the standard yard preserved in the exchequer chambers. In France and in other countries which have adopted the metric system, it is the meter. The meter is theoretically the 10 millionth part of the length of a meridian of the Earth measured from the pole to the equator. But practically, it is the length of a standard preserved in Paris, which was constructed by Borda to correspond, when at the temperature of melting ice, with the value of the preceding length as measured by Delambre. That's not clear at all, but something to do with the temperature of melting ice. The meter has not been altered to correspond with new and more accurate measurements of the Earth, but the arc of the meridian is estimated in terms of the original meter. Yeah, I'm wondering if anyone knows what that ice part is. Please let me know in the comments. Let us all know. In astronomy, the mean distance of the Earth from the Sun is sometimes taken as a unit of length. In the present state of science, the most universal standard of length which we could assume would be the wavelength in a vacuum of a particular kind of light emitted by some widely diffused substance such as sodium, which has well-defined lines in its spectrum. Such a standard would be independent of any changes in the dimensions of the Earth and should be adopted by those who expect their writings to be more permanent than that body. In treating of the dimensions of units, we shall call the unit of length L. If L is the numerical value of a length, it is understood to be expressed in terms of the concrete unit L, and that he's got that capital. So we're going to call the unit of length, that's capital L, and then lowercase l is the actual numerical value. Time. The standard unit of time in all civilized countries is deduced from the time of rotation of the Earth about its axis. The sidereal day, or the true period of rotation of the Earth, can be ascertained with great exactness by the ordinary observations of astronomers, and the mean solar day can be deduced from this by our knowledge of the length of the year. The unit of time adopted in all physical researches is 1 second of mean solar time, mean meaning average. In astronomy, a year is sometimes used as a unit of time. A more universal unit of time might be found by taking the periodic time of vibration of the particular kind of light whose wavelength is the unit of light. We shall call the concrete unit of time T, that's a capital T, and the numerical measure of time T, lowercase t. Mass. The standard unit of mass in this country, and he's writing this from America, by the way, the avoirdupois pound preserved in the exchequer chambers. The grain, which is often used as a unit, is defined to be 7,000th part of this pound. I actually have to check. He might be British. I thought he was American. No, I'm not sure. In the metrical system, it is the gram, which is theoretically the mass of a cubic centimeter of distilled water at standard temperature and pressure, but practically it is the 1,000th part of a standard kilogram preserved in Paris. The accuracy with which the masses of bodies can be compared by weighing is far greater than that hitherto attained in the measurement of lengths, so that all masses ought, if possible, to be compared directly with the standard and not deduced from experiments on water. Actually, I think he is British because this was published in Oxford and he's saying this country, so I'll double check after this. Hopefully you all are looking him up too because he's super awesome. In descriptive astronomy, the mass of the sun, or that of the Earth, is sometimes taken as a unit, but in the dynamical theory of astronomy, the unit of mass is deduced from the units of time and length, combined with the fact of universal gravitation. The astronomical unit of mass is that mass which attracts another body placed at the unit of distance so as to produce in that body the unit of acceleration. In framing a universal system of units, we may either deduce the unit of mass in this way from those of length and time already defined. And this we can do to a rough approximation in the present state of science, or if we expect soon to be able to determine the mass of a single molecule of a standard substance, we may wait for this determination before fixing a universal standard of mass. I'm not sure if that was done in the 150 years or so since he wrote this. Very well could have been. Finding a rough approximation of a single molecule of a substance. Most likely that's been found. We shall denote the concrete unit of mass by the symbol m, he's got a capital M, in treating of the dimensions of other units. The unit of mass will be taken as one of the three fundamental units, which we have, the other two were, the three fundamental units. He has length, time, and now he's adding mass, like the weight. Okay. So we have L, T, and M now. Okay, so the unit of mass will be taken as one of the three fundamental units. When, as in the French system, a particular substance, water, is taken as a standard of density, then the unit of mass is no longer independent, but varies as the unit of volume. If, as in the astronomical system, the unit of mass is defined with respect to its attractive power, the dimensions of capital M are, oh, we've got the first equation here. The dimensions of M are L cubed, capital L cubed, so the length cubed, times time to the negative 2. The dimensions of M. For the acceleration due to the attraction of a mass, lowercase m, at a distance, lowercase r, is by the Newtonian law m over r squared, so mass over the distance squared. So that's the acceleration due to the attraction of a mass m at a distance r. So that's a Newtonian law, m over r squared. Suppose this attraction to act for a very small time, t, lowercase t, on a body originally at rest, and to cause it to describe a space S. Then by the formula of Galileo, S, so we're starting getting the formulas. It's a space. S equals 1/2 t, oh, sorry, 1/2 f times t squared. So what's f? We didn't, this is where it might be time for me to do an episode where we go through the physics notation, the symbols one by one. So this is the formula of Galileo. I'll just show it to you, right? This is where we're at. So, starting to get heavy with the formulas. This might be a good place to take a break, because I think from here on out, it gets in. Okay, this is the last page I printed because I saw that it was getting into formulas. So I'll just complete the page after that formula. So, since R and S are both lengths and T is a time, this equation cannot be true, you know, R being the distance, and I don't know if he said what S, oh, space, S is space. Okay, so the distance and space. So now what did he mean by space? Space S. Sorry, I'm already getting a little bit confused here, so it's definitely a good time for a break. but basically it just says, since r and s are both lengths and t is a time, this equation cannot be true unless the dimensions of m are L cubed times t to the negative 2. The same can be shown from any astronomical equation in which the mass of a body appears in some, but not in all of the terms. Alright, so yeah, definitely time for me to go and start digging into what exactly this means. But I'm on, you know, like I said earlier, I'm on a roll with these videos and just figure keep going when I can. It's kind of a lull in some of the other areas of interest in my life right now. So, as always, hope some of you enjoyed, at least. If you made it to the end of the video, you may well have. As always, so much love, and may you all be true to yourselves. May we remember how to be our most authentic beingness, because it's really actually the most fun. And I just hope you all are loving life and taking everything moment by moment, because it's all that's ever real. Myself included, I've been reminding myself of that a lot lately. It's just moment to moment, and there's not really anything ever to be afraid of when we're present in the moment. So, alright, take care.